started since long before I arrived here last year. We have a couple of our team members here in the audience who've been doing this work on the ground that will really help build what we call resilient reefs of the future. So to start off with, because I want it to be a little interactive, does anybody have a sense for what we mean by resilient? Yeah.
We can withstand higher temperatures, perhaps, and higher acidity.
Yeah, absolutely. So we'll talk a lot about those things today. So that kind of actually hits on a term I like to call resistant. So they might be resistant to warming and acidification, but if they're bounding back, they're recovering from that stress, then they're resilient. So very similar to how we are going to experience stress, and climate change is going to dictate our future, and it might be different, and very possibly will be different from what it is today. But we hope that our reefs can be resilient and that they'll persist through these stresses and still exist for our kids and their kids and so on. And so that's what really I'm going to talk about today, is what reefs are going to experience and hopefully how they might persist in the future. So to start off with, we always like to start with what is a coral. So this is a beautiful image we always like to use of a coral organism. So I'm kind of hinting at it, but what is it? Is it an animal? Show of hands. Is it a plant? Is it a rock?
Is it both?
I noticed that Katie there, the manager of marine systems here in our project, has raised her hand for all three.
Yeah.
It's kind of a trick question. They are actually animals, so that's the strict definition, so you guys all got it right. But you'll notice that they have this really green pigmentation in their tissue. And so this is actually a symbiotic algae that lives in their tissue. It's a single-celled organism, a dinoflagellate, that photosynthesizes, so it uses carbon out of the atmosphere to create energy. And actually most of the energy that the coral needs comes from these symbiotic algae. They're super, super important for the coral organism. But they're also rocks in some ways. So corals, they grow really fast, and they secrete their own skeletons made out of a substance called calcium carbonate. So this is what you find on the beach, in the rubble, along with the shells and the sand that you might collect. So this is the skeleton that the coral creates, and this is incredibly important, and we'll come back to why in a little bit. So this is the sad part of the talk, but we want to start off with why this is important and why we care. So unfortunately, coral reefs worldwide are under extreme threat. So some estimates are that we've lost as much as 50% of the world's coral reefs. So this is an extremely dire situation, which is why our team has amassed collaborators from all over the world, 40 institutions around the world, the best coral reef scientists, to really start to try to tackle this problem. So really the problem stems, as we've already heard from our guests here in the back, because the oceans are warming. And one of the big factors that happens when oceans warm, so when we get these really, really stressful temperature events, corals undergo a phenomenon called coral bleaching. And you've probably heard of this, and it's as aptly named as it sounds. So corals that are healthy here on the left, that have this really brown or very beautiful, sometimes even blue colors that are given by the symbiotic algae that live in their tissue. They release that algae. So there's actually free radicals, so these really harmful chemicals that build up in the coral tissue. Corals get really stressed out and they say, sorry, you're no longer welcome here, and they throw out these algae, leaving behind this rock, this calcium carbonate material that we talked about earlier. So although the coral is still alive at this point, you're seeing through that clear tissue to the rock beneath it. So why is this happening? So fundamentally, this comes back to the fact that our oceans are warming. So I've actually plotted here surface air temperature around the world. This is an average. It's plotted as an anomaly, so a departure from the pre-industrial temperature that we had here on Earth. And so you can see that we've warmed as much as almost a degree around the world. And our oceans have simply warmed. And this is not a climate change talk, so I'm not going to focus too much on this, but I want to emphasize this is fundamentally because we are burning fossil fuels and we're adding CO2, so carbon dioxide, into our atmosphere. So warming is happening as a function of the rate of what we're burning and putting into our atmosphere. So in terms of corals, this has led to an increase in the frequency and intensity of these bleaching events. So now plotted here along with the surface air temperature is the frequency of these bleaching events. And I will note that the observations started in 1960, so that's part of the reason why there's nothing here. But you can see this really ramp up, this really extreme increase in the number of events that we've experienced. Of course, part of this is observational. We have more divers in the water that are aware of bleaching, that are observing these events. But a lot of this is real. So you'll notice this huge, there's almost 2,000 observations from the 1997-98 year. And this will become a theme throughout the talk, but it's because this was an El Nino year. So this was a climate event that was a particularly warm year, and it was warm throughout the world's oceans, and we had a huge amount of coral bleaching. So coral bleaching does not mean death necessarily. Corals can regain symbionts, or they can even do what we call shuffling, which is sort of upregulate and have more of the somewhat rare types of symbionts that live in their tissues become more prevalent following bleaching. And so you can actually get recovery. But often, following a bleaching event, you can get algae-covered reefs within a year. So if they do not recover the symbionts within their tissue, within 1 year, that coral often dies. And this is, I will point out, amazing imagery from Catlin's Seaview survey. If you ever just want some beautiful imagery of corals, both alive and depressing, the pre-post bleaching event I showed earlier is also from their surveys. So the other main driver, is he pointed out as well, is ocean acidification. So in addition to the CO2 that's being put into our atmosphere, a lot of it is actually taken up by our world's oceans. So the more and more we emit, the more and more oceans are taking up. And going back to gen chemistry, when you put CO2 in water, they react, and you get a weak acid, carbonic acid. So as a weak acid, what that means is that it partially dissociates. So you end up with one hydrogen ion still left on the bicarbonate and a hydrogen ion. And then it can dissociate again into carbonate and more hydrogen ions. So remembering it back to gen chemistry again, is pH is a function of the log of the hydrogen ions. What this means is our oceans are becoming more acidic. So this is what acidification means, right? They're moving towards a greater and greater acidity. Okay, so what does that mean for corals? So not only are the oceans becoming more acidic, but come back to that skeleton. The skeleton is fundamentally made out of calcium and carbonate ions. So if we come back to this previous figure, we really need these CO3 or carbonate ions for corals and other calcifying organisms to grow. So these are really important. So it turns out that not only are oceans becoming more acidic, but as they do, the type of carbonate that is dominant in seawater changes as the pH changes. So that's what's plotted here. So on the x-axis is the pH of water, and on the y-axis is the fraction of dissolved inorganic carbon. So all this is the acid, the bicarbonate, and the CO3 or carbonate ion. So again, all I want you to take away from this is what corals need in green, the CO3. Today, ocean pH is about pH of 8. And you'll notice that almost all of the ions in solution are bicarbonate. So there's not actually that much carbonate for the corals to use to begin with. It's about 10% of the DIC in water. And as oceans become more acidic, this balance shifts towards lower and lower carbonate ions, meaning it gets harder and harder for corals to grow. So this is really important. Instead, we get more and more dissolved CO2. Okay, so where are we going from here? So this is a graph from the Intergovernmental Panel on Climate Change, and all I want you to take away from this is that the future is in our hands. So where we go from here is what a function of what we do in terms of burning fossil fuels and increasing CO2 in the atmosphere. So we have many futures. We could go to net zero emissions by 2080, which is what's shown in blue, and some various simulations around that average. We could be on this trajectory, or we could be on the trajectory of business as usual, which is precisely where we are right now. So the red here is us. So just to put this in perspective, so this y-axis here is the emissions in gigatons of carbon, so billions of tons of carbon each year. And the projected 2016 estimate is here. And here's where we were in 2018. 37.1 gigatons of carbon emitted in the atmosphere in 2018. So this is the depressing part of the talk, is that we are on the worst case scenario. And you can hear my voice shaking a little bit because it means a lot to me, right? And a lot of us in the room. Okay, we're almost done with the depressing part, I promise. Then we'll get to the hope. So what does this mean if we keep going into the future? So this is where climate models come in. And so this is now 2000 is here and 2500. We often project out to 2100 here in the middle. On the top is the carbon dioxide in parts per million that I just showed. And the bottom is the warming in degrees Celsius. So again, the red here is our current trajectory as business as usual. So today, if you are like me and check this regularly, the CO2 concentration in the atmosphere is 408 parts per million, right here on November 7th. And sort of shifting to what the biosphere has done to really contribute to what we know and why there's hope. There were some really seminal experiments that were done in the 1990s and early 2000s that increased the CO2 in the atmosphere and the pH, decreased the pH of the Biosphere 2 ocean to mimic what we thought was the doubling of pre-industrial CO2. So that's 560 ppm. And Chris Langdon, a Columbia University researcher, found that biosphere corals grew up to 40% slower under this concentration of CO2 in the atmosphere. So the bottom line is we know, and we know because right here in Arizona in the Biosphere 2, Chris Langdon did these experiments, that corals will grow slower under lower pH oceans. Sorry. And on our current trajectory, this scenario could happen as early as 2050. Okay, so now let's shift to why we should care and what we're doing about it. So we're here in Arizona. We're very far from coral reefs. So most of us probably think of a reef, we think of this. Maybe in our dentist's office, maybe at home, but we think of an aquarium reef. Very beautiful, vibrant, full of beautiful reef fish. And so we fundamentally care because they're beautiful. Who here likes to snorkel or dive? Awesome. So those people raising their hands, you might also care because you've been to a reef, you've seen a reef, and you've fallen in love with a reef. And you really want to make sure that your children or your grandchildren have the opportunity to have those experiences. This is me diving in the Galapagos. But for the rest of the world, and for all of us, the reason why we should care is because they are a tremendous hotspot of biodiversity. So if we don't protect corals, we lose hundreds of thousands of species, depending on how bad it gets. And this is because corals have this amazing 3D structure. So we like to make an analogy to a city of New York. Like New York City, it can house millions of people because there's all sorts of nooks and crevices and floors and underground subways and all of those sorts of spaces, those habitats, those ecological niches exist on a coral reef. And this is why they're such a hot spot for biodiversity. One example is fisheries. So we always think about the world's fisheries And what we don't really realize is that almost all economically important fisheries spend some portion of their life on a coral reef. However, this is typically what comes to mind when we think of fishing, at least it does when I do. These really big game fisheries where people are going out much like hunting and trying to get the biggest fish they can. Or on the right, these sort of commercial expeditions that bring us the tuna, the mahi, or whatever that we really enjoy to eat in first world countries. But for much of the world, fisheries looks like this. And this is a picture that I took in the US Virgin Islands, and this is what they're eating. This is sustenance fishing. This is people going out and bringing dinner home to their family. And so fishing supports millions of people living within a striking distance from coral reefs worldwide. And finally, coming back to that structure, they fundamentally create a barrier that is the last line of defense to our coastal cities. And millions of people, if not billions, depending on your estimate, live within the threat of sea level rise. And so really corals are fundamental for protecting our cities into the future. So it's really hard to put a dollar estimate on this much socioeconomic value. But there's been a lot of studies done on this, and they estimate that about $1.2 trillion, or $200,000 per hectare of reef, of critical goods and services are given to us by our coral reefs. So on a personal level, I'm here because I was fortunate enough to have that experience of snorkeling and diving at a relatively young age, mostly because I grew up in Minnesota, and my parents were really sick of the cold by the time I'm the youngest of four. So on the left here is me and my father snorkeling, about to snorkel in the US Virgin Islands. And I went back as a fellow for the National Marine Fisheries Service less than 5 years later, and after this trip we went back a few times, I got a little older. And unfortunately I couldn't contain my excitement to go back to these reefs. They were really where I fell in love with what I do. And I got in the water and my snorkel fell out of my mouth because everything was just dead. And I still can't talk about it, and I'm gonna tear up a little bit here, but it's here I was in my 20s, and I had experienced complete loss. And so shifting forward, and I promise you this is the last of the depressing sides, I now poke holes in them because I know that this global change is what's driving their demise. And we can only find solutions by looking into their skeleton and using the biosphere to test really innovative solutions. And so that's what I want to talk to you about for the remainder of the talk. Okay, so why is there hope? Moving to the fun part. So luckily decades of coral reef research has taught us that there are resistant corals. There are corals that can resist warming and acidification better than others. And there are algae, this symbiotic algae that live in their tissue that can resist bleaching better than others. But there are parts of the reef that can do better than others. So the forereef, the front of the reef, does worse than the lagoon, where lagoon temperatures are changing rapidly on a day-to-day basis, so they're used to warming. And finally, where my research really comes in is we know what parts of the world's oceans are more likely to resist bleaching and be resilient to climate change than others. So in other words, we've really learned the building blocks or the pieces of the puzzle that can build resilient reefs of the future across scales, everything from the micro scale to the global scale. So I have to talk a little bit about what my group does at main campus in Geoscience, and this is that we can learn a lot from history. So it turns out that these El Nino events, these large global scale climate events that drive warm waters across the Pacific and around the world, impart some resistance on corals. So if we look, what's plotted here is a map of the temperature at which corals bleach. And so over here in the Western Pacific, you'll see that if it gets about 0.5 to 1 degrees above normal, corals will bleach. But you'll see here in the Eastern Pacific that it takes 4 degrees Celsius in some locations before they bleach. In other words, it takes a lot longer for them to bleach because historically they've gotten slammed. They get hit over and over and over again, and we know that this imparts resistance. So I really love this quote from a paper that was subsequently published after I did that work, because it really has dictated where my career has gone. The results identify the importance of the Equatorial Pacific on research on coral reef resilience under a warming climate. So now a lot of what my group does is actually looks at Pacific climate and tries to better understand how the Pacific is going to change with warming, so we can know how history might shape the future. So how do we do this? Here in Arizona, the world's leading tree ring lab, you guys I'm sure have heard about this, but we can use tree rings to look at how precipitation and temperature has changed in the past. So my group uses a very similar approach using corals. So here I am in the Marshall Islands standing on top of a fossil coral, so meaning that it died before I got to it. And actually it flipped on its head, so I'm standing on the base of the coral. And if you squint, maybe, you can see rings going down the coral. So if I zoom in here, you can probably see them a little bit better. So here I am actually now drilling the coral and going down to the base and getting a core of the history of the ocean conditions that that coral experienced. So this is a great time-lapse video that my graduate student Emma Reed created of us drilling that coral in the lagoon of Majuro Atoll in the Republic of Marshall Islands. So you can get a sense for it's a long process, and it's unfortunate that her memory filled up before we finished, because you could see the tides slowly increasing, and eventually Emma and Hussein were floating and handing me equipment. And so finally we had to bail and finish the next day. Okay, so if we split open one of these cores, and I have a bunch of them up here, you can take a look after the talk, we see bands, just like we do in the rings of a tree. So corals grow, and we have seasonal bands, and so we can actually get seasonal climate records going back to as long as that coral lived. So what we do in my lab is we take samples going all the way down the core, and we use the geochemistry of the skeleton to tell us about the ocean conditions of the time that they grew. And so for one of the interactive portions of my talk, I've been working with an art student on campus to create a 3D model of a coral that we would take a sample from. And if you pull out the core in the middle, it has alternating banding, much like the figure you see up top. So I'm really proud of that. She did an amazing job, so take a look for yourself and please pass it around. So because I just told you that I do this because I'm trying to protect the reef, I want to just have a quick aside to say that this doesn't kill the coral. And in fact, what we do to protect it from getting other organisms from sort of eroding it out from the inside is we put these cement plugs in the top of the core and sort of beat them in with a hammer, and then it just grows right back over that surface. Okay, so I'm not going to talk much more about what my group does on campus, but I just want to give you a couple examples of what we can learn from this type of work. So one of the questions that Emma Reed is tackling is, from using these corals from the Marshall Islands, is how much will sea level rise within this century? How much has it rose over the last 100 years? And finally, arguably the biggest question that we try to answer, and probably will for the rest of my career, so it's good job security, is what is the fingerprint or the imprints of warming in the tropical Pacific, which is the world's heat engine. If we don't figure out what's going to happen to the tropical Pacific, we won't know how climate change is going to unfold. So I'll give another talk in about 20 years and hopefully I'll have an answer. So I just want to point out that this is all work that my incredible group shown here up top is doing. Emma Reed, Alice Chapman, Maria Schneider, Brianna Holger, and Julia Bateman. They're fantastic, and so I hope that they'll give another talk and talk more about their research. Okay, so finally, I want to end by the hope part of the story. So obviously, it's really hard to work in coral reefs and climate change right now. But I'm back here in Arizona because I really believe in this biosphere project, and I really think that this is the answer and how we're going to solve this really big crisis. So to kind of, one last sort of nugget from my work is one of the reasons I personally have hope is that I've gone to all these sites, I've poked holes in corals, and over and over and over again, I see them recover. And this is what that looks like. So these are two colonies from the Galapagos Islands, so the far eastern Pacific. And in 1983, there was one of these really big El Nino events. And corals everywhere, it doesn't matter where we core in the Galapagos, they all died. It was ugly. I mean, they all died. It was one of the most catastrophic bleaching events we have. But this is where the hope comes in. They recovered. So they continue to grow. After they had this death horizon, where we have, this is actually a shell of a bivalve that grew over the top of the dead coral. And then it recolonized, and it kept on fighting. And so here's where the hope comes in, is if we can tackle climate change together, and if we can come up with solutions right here in the Biosphere 2 ocean to buy corals some more time, we can have reefs in the future. So it's up to us to do those two things. And again, we have the pieces of the puzzle. We've done our homework. Decades of research, we've done our homework. Okay, so how are we gonna do this? So this is my little kitschy animation, for I feel like I'm gonna take everything that we've learned across the Pacific, and we're just gonna shove it into the Biosphere 2 ocean. And we're gonna stop working in our little labs, and we're gonna stop working on process, because we understand process. We know why corals bleach, we know how they bleach, we know when they bleach. And now we're gonna say, we're gonna move from process to doing something about it. And so the coral reef community now recognizes it's too late. So this is why we've amassed such a huge amount of collaborators. So fortunately, too, we have just the right collaborators. So our partners around the world have come up with really innovative ways to not only apply these processes, but actually speed it up a little bit, make corals a little bit more resistant to warming than they would have been otherwise. So these are some of the main partners, Marine Laboratory, Australian Institute of Marine Science, and Hawaii Institute of Marine Science. Okay, so what are they doing? So one of the big things you've probably heard about in the news is that coral reefs can be restored. And so this is a process of breaking corals up into small little nubs. It's a process called fragmenting, not to be confused with fracking. Fracking, bad, fragging, good. I'm just kidding, I shouldn't say political things. Sorry, edit that one out of the Facebook Live, please. Anyway, so fragmenting corals, it turns out they actually grow faster when we do this. And so then we can transplant them onto the reef, they're growing faster, and they reseed these reefs. So this is a species, Acropora cervicornis, which was on the endangered species list because it was so degraded. And Mote Marine Laboratory has single-handedly restored many reefs in the Florida Keys. And they've seen up to 95% survival following 1 year later after reseeding these reefs. So it's not like they're putting them out there and they're dying. So it's incredibly promising. However, we don't know what's going to happen going into the future. Unfortunately, even if we were to stop emitting CO2 tomorrow, our oceans are going to continue to warm. There's some inertia in the system. So we need to know what's going to happen. Oops. Oh no, it's not playing. The Okay, I have a really cool aerial video of Biosphere. Hopefully, has anybody been to Biosphere? Yeah, fantastic. So you can imagine what it looks like.
Oh.
And I'm very sorry it's not playing. So we know that they work now, but we need to know whether they'll work into the future. And this is where we need a place to test these solutions at scale, so meaning at a reef ecosystem scale, so that we know what solutions will work and what solutions will give us that resilient reef of the future. So, fortunately, we have the world's largest ocean reef lab, 700,000 gallons, dedicated completely to reef research. So at this scale, unlike a laboratory experiment where a lot of these innovative solutions have been developed, we can actually get natural intrinsic interactions among species. So we have herbivores, fish, invertebrate grazers who are feeding on the algae on the reef. We have microbes that play a really important role in reef health. And critically, we also have control. So this control comes with the help of many generous supporters of this project and some grant support to really redo all of the life support systems of the Biosphere 2 ocean. So we're bringing the system from the 1990s when it was first built up to the 2020s. So this is an example behind me is a heat exchanger. So it allows us to really precisely control the temperature of that 700,000 gallon system by 3 degrees Celsius, or sorry, 2 degrees Celsius or 3 degrees Fahrenheit every single day.
Wow.
It is amazing. It is beautiful. Titanium plates. If you ever want to come, just take a look and be in awe with me. We can do that. It's incredible. So this is now online and we're doing testing as we speak. The other thing that will be a big change for those of you who have been to the Biosphere 2 ocean is that we're going to add a series of trusses to put lights over the system. So again, they have symbiotic algae in their tissue. They really need light to be healthy and happy. So this is just what that looks like. This is a cross-section of the bottom of the ocean and what it looks like. We have the deepest portion over here on the right and a reef crest and a back reef lagoon. So it looks just like an ocean does in real life. And hanging over the top of the main reef crest will be up to 288 halogen and LED lights. So this is going to be a major overhaul, and we're still working on funding for this. So, but hopefully in the coming year we will be able to renovate this part of the system. So this is a 3-part project, and over the past year our team has been working on phase 1, which is to really rejuvenate and remediate the existing system. So the saying goes, you know, life gives you lemons, make lemonade. This is our reef version. The system looks like it does on top right now. Those of you who have been there recently have seen this. This is an image of what reefs could look like in the future if we do nothing, covered in algae. So for us reef scientists, it's an opportunity to say, how do we get from this back to this? How do we remediate or rebuild a degraded reef system? So sorry, one more kitschy animation. So I'm just going to show you what this looks like. So if we sort of zoom in to the bottom of the reef and dive in for a closer look. Our team, and these are the real heroes here, both Franklin and Katie are here in the audience, have been monitoring this system very closely. So again, the bottom is completely covered in algae. This is Franklin holding up a big algae ball in the ocean. So we've been monitoring all the physical and chemical parameters of the reef. So we have this instrument in the deep part that measures the abiotic controls, so temperature, pH, chlorophyll, salinity, etc. We painstakingly take samples multiple times a week to look at the nutrient concentrations as well as the microbiome. So one of the really key aspects of reefs is that we don't actually know how the things that we can't see, these little single-celled organisms, control reef health. So this is really where the Biosphere 2 project comes in. This is an opportunity for us to understand how these things that we can't see are dictating the reef health. And then finally, we can't forget about our charismatic macrobiomes. So we're also, of course, looking at the algae and the invertebrates and fish and so on. So here's some pictures of what that looks like. Again, this is the same picture of Franklin with some of the algae. Here's some of the eukaryotic microbes. So these are diatoms, and we have dinoflagellates. And we just hot off the press found out from our collaborator Jeremiah Hackett that there are still symbiotic algae from the corals that grew in the Biosphere 2 ocean in the 90s. So exciting. So that's our biggest news. So that's really cool. And this probably won't play either. Darn. So this is a really cool animation fly through of a stitching of images by our collaborators at Scripps of what the benthic habitat looks like in the Biosphere 2. For those of you who are interested in our amazing videos, I'll be happy to show you after, and they'll hopefully work. Okay, so finally, last graph of the talk. I wanted to show you an example of some of the really exciting results that we have coming off this part of the project. So a lot of what I do in the coral skeleton, we can also do this in sediments, is use geochemical signatures of the ocean conditions in the past. So we had an RU student here, up here at the top, Jake, who was took a core with us in the Biosphere 2 ocean, and we wanted to know, can we use some of these signatures to look at the degradation of the Biosphere 2 ocean since the 90s to today? Is this a good way to measure reef degradation? And it was like even better than I could have even imagined. So basically this isotope ratio I won't get into really records this healthy reef with normal trophic dynamics, fish and corals and algae, all the way down to this green algae covered reef that we have today. So these are the types of things that we've been doing over the past year. So then we have moved rapidly into the remediation stage, and actually I have a video that will probably also not work of Katie and Franklin literally today pulling some of that algae by hand. But we're trying to our goal is to have corals in the Biosphere 2 ocean by next year. So that means we have to pull out some of those algae. So what have we been doing to do this? So first, starting in April of last year, we introduced some new herbivores and invertebrates in the system that also feed on algae that can help us sort of quite literally chew away at the algae on the reef. And unfortunately this isn't enough, so we are now manually removing this algae, which was expected. There is a lot of algae. And then finally we're going to black out the reef to get rid of any final algae spores in the system. And of course, all this time, it's a scientific reef, so we've been doing all the same biogeochemistry on the side as we do all of these things. So here's some of the critters that we introduced. So this was a lot of work this last year. The invertebrates here on the top, and our charismatic fish here on the bottom, ocean surgeonfish and red-banded parrotfish. So if you haven't been to the Biosphere 2 ocean recently, I urge you come back. It's always changing. So our most exciting feat, which as Katie shakes her head, was quite a feat, was the fish introduction. So in April, the fish arrived at 1 p.m. off the flight to Tucson from Florida. Katie and Cara picked them up, and by about midnight, the fish were successfully released into the biosphere. And of course, again, it's a science experiment, so Erica swabbed each one of the fish to look at their microbiome, what were they introducing into the system. We weighed each and every fish, etc. Oh, it worked! One video worked!
Yay!
So here's just literally today, this afternoon, Franklin, Cara, and Katie removing algae from the Biosphere 2 ocean reef. So you can see it piling up more and more here. So I mean, like tons of algae. It's insane. It's so much work. And they are heroes because they have done so much of it already. So a little bit less to do for next time. Okay, so then phase 2, which will start hopefully next year, it really depending, to be quite frank, funding to implement the rest of our engineering, is we will move into the second phase where we're going to really test these innovative solutions that our partners have come up with. So things like, I'll show you, add beneficial microorganisms to make corals more resistant to stress. We can test really novel substrates. What are the particular substrates that really work for reef restoration? One of the things we're most excited about is we can do something as simple as bring species together that have never been together before. Because unfortunately with climate change, ecological niches, ecological barriers, they're going to change. Reefs are going to be different. So what happens when those species come together? And finally, some of the more sort of novel and potentially risky solutions that need a home in the biosphere situation to test are things like stress hardening, where we purposely stress corals and we make them more resistant to stress. And we can also hybridize corals in a way that we have with agriculture to make them even more resistant. So this is an example of Erica Santoro isolating beneficial microorganisms from corals that we received from Hawaii this past spring. And so you can, she's rinsing them, and then she isolates the microbial community on petri dishes and then looks for their beneficial quantities using a suite of molecular techniques. And then we can apply these to the corals that are arriving in the biosphere as early as January, fingers crossed. So really the question that we're hoping to answer over the next 5, 10, however long it takes us, years, is how do we best build a resilient reef of the future? And what does that look like? So first, thanks to some really generous donors and a team that's willing to, quite frankly, do anything, including solder off a door, we have transformed in the last year the old scrubber room to a beautiful raceway experimental system. So we'll have up to 5 of these experimental tanks. They hold 2,700 liters. And will be where we can stress harden corals, where we can hybridize corals, add probiotics, and so on. And then finally, the last part is that we are going to, of course, warm them. We're going to lower the pH. We're going to acidify the reef, just like Chris Langdon did decades ago, or decade and a half ago. And we're going to see what actually works into the future. So with that, I just want to say that I'm up here giving the talk, but I couldn't do this without the team that's on the ground doing all the hard work up here at the top, as well as our advisory board and our amazing partners all over the world. And of course, funding my group on campus, partners, and so on. And with that, I'll take